So let's continue our discussion. Let's come to question number 76. Which compound among the following is not an aromatic compound? So here we have to figure out that it is asking about the compound which is not aromatic. Okay, so here if you will see, aromaticity is decided by 𝐭𝐿 rule. Okay, if you see the 𝐭𝐿 rule, this rule says the electron must have 4n plus 2 pi electrons, and in addition to that, prior to that, the molecule should be planar, it should have complete conjugation. Okay, so if you see here, the compound is completely planar here, and it is having complete conjugation. You can see the negative charge in conjugation with the pi electrons. So let's count the number of pi electrons here. We'll have 2 pi electrons for this bond, 2 for this bond, and 2 here. So we have 6 pi electrons which satisfies this 𝐭𝐿 rule. So we can say 6 pi electron means the compound is going to be aromatic. Come to the second part. Here, if you will see, again there is the planarity and complete conjugation of the charge and the pi electrons. So here, if we will count the number of pi electrons, like you can see, each double bond will have 2 pi electron, and this will have again 2, and this will have 2, and positive charge means vacant orbital, means there is no electron. So how many electrons are there? It is 6 pi electrons. Again, this compound is aromatic. Okay, next let's come to part 3. Here again you can see the molecule is planar. It is having complete conjugation of electrons, pi electrons. You can see the pi bond and the positive charge present at alternate position. So that means we need to count the number of electrons. Here you will see there are 2 electrons present. Since we know that this positive charge means no electron, that is just a vacant orbital. So here you can get 2 pi electrons, which means this compound is again aromatic. Well, so let's come to part 4. We got our answer, but still let's see that why this compound is not aromatic. I found this thing. See this carbon. This carbon is actually sp3 hybridized. That means there is no chance of this to be planar. This sp3 hybridization brings tetrahedral geometry. That means that is going to be non-planar. So definitely we have our answer, and that is number 4. This is not an aromatic compound. Let's move to the next part. Given below are 2 statements. Statement 1. The boiling points of the following hydrides of group 16 elements increases in the order water, H2S, then H2Se, and then H2D. So we have H2O, H2S, H2Se, and H2D. These are all the atoms from oxygen family. Okay, their hydrides are there. Statement 2. The boiling points of these hydrides increase as the molar mass increases. That is the meaning actually. So here we'll see that water is quite different from all these hydrides. It's because of hydrogen bonding present there, and that hydrogen bonding increases the intermolecular forces, and that increases the boiling point. So water has the maximum boiling point, and as you know that water exists in liquid state at room temperature, while H2S is a gas. So here water should have been present here at the it should have the maximum boiling point. So this option is incorrect. The rest orders are correct because we decide that on the basis of the molar mass. Here second part, it's given that it's directly related to molar mass. So no, it's not completely correct because water has hydrogen bonding. That is a different a factor we are considering. So here both the options seems incorrect. Okay, so statement 1 and statement 2 both are incorrect. So answer is second. Let's come to the next part. Let's see what we have there. A match the column. List 1 and list 2, and we can see the metals out here, and here a base, and there we have different applications of these metals as well as the KOH molecule. So here if we'll see lithium, so most of you would have seen that the lithium ion battery is present mostly in phones and electronic devices. So basically it has application in the electrochemical cells. So lithium, it will be used in electrochemical cells. Second, sodium. So basically sodium is used as coolant in nuclear reactors. And here sodium is taken in the liquid state, and that proves to be a better coolant than water at higher temperature. So here we can say sodium can act as a coolant in fast breeder reactors, which are nuclear reactors. Next is KOH. So KOH, as we know, is basic in nature, and that is why it is a it absorbs carbon dioxide, which is a acidic oxide. So here we can say it's going to be this, and the last one, cesium. Photoelectric cell. Why? As you know, cesium has a very low ionization energy, because of which it has a very good application in the photoelectric cells. So basically we can say that these are the options. So we can check lithium 2, that means A2, and B is 3. A2, B3. We got our answer, but still let's check C1 and D4. We have option 4 as correct. Okay, so let's move to the next one. 79. Which of the following sequence of reactions is suitable to synthesize chlorobenzene? First of all, you should know what a chlorobenzene molecule is. It is just this. So you have to prepare this, and we have different methods. Let's check out which one is the correct one, which one is the most appropriate one. So first of all, it is benzene with chlorine and anhydrous FeCl3. As you all know, FeCl3 is Lewis acid, and we have Cl2, that means Cl2 with Lewis acid. We have seen it somewhere, right? We have seen it in the electrophilic aromatic substitution, where chlorine gets substituted on the benzene ring. So here we have benzene, let's say we have benzene, and we take chlorine with some Lewis acid. Here the acid is FeCl3 ferric chloride. So that is definitely going to give you chlorobenzene. So that is correct. That seems to be the right method. Let's check another one. Phenol with NaNO2 HCl and then CuCl. No. Phenol with NaNO2. No. It should have been like, if you want to prepare diazonium ion, then it should have been aniline. So this cannot be correct. Next, benzene with HCl. So let me tell you, alkene reacts with HCl because it is better nucleophile, more nucleophilic than benzene. Benzene is not that nucleophilic because it will lose aromaticity, and hence it will lose the stability. Next is aniline with HCl. So base and acid reaction simply will form aniline chloride. Okay, so this is not going to be correct. The correct answer is option number 1. Let's move to the next one. So a long question, again the statement 1. Given below are two statements. Statement 1. The boiling points of aldehydes and ketones are higher than hydrocarbons of comparable molecular masses. Okay, so this I think is correct. We all agree that aldehydes and ketones have higher boiling point than the hydrocarbons. You can see here we have hydrocarbons and we have aldehydes and ketones. That means we know the intermolecular force in aldehyde ketone is dipole-dipole interaction, which is better than hydrocarbon because we have London dispersion forces here in hydrocarbon, but which is not that much stronger in comparison to the aldehydes and ketones. But still, I'll say that in aldehydes and ketones, the dipole-dipole forces, they are also not that strong. They are weak forces. So we can say this is correct. And next, because of weak molecular association in aldehydes and ketones due to dipole-dipole interaction. So weak molecular association, dipole-dipole interaction, correct? So this statement is correct. Next, move to the statement 2. The boiling points of aldehydes and ketones are lower than the alcohols of similar molecular masses due to absence of H. So we know that when we compare the boiling points, we take compounds of similar molecular masses, and it is same as taking, like, if you see some wrestling competition, you see that the weight category is there. So here also we have the same category, and we can see that we are taking off aldehyde ketones and alcohols of similar molecular masses. So we can see in alcohol, like we have ROH, and we have another molecule right? I can draw it like this. So we can see here we have interaction, that is hydrogen bonding. But in aldehydes and ketones, we have dipole-dipole interactions. So hydrogen bonding is much more stronger than the dipole-dipole interaction, and that is why alcohols have greater boiling points than the aldehydes and ketones. So I think statement 1 is correct and statement 2 is correct. So both are correct, and I think it's undoubtedly option number